understand what is computational train aerodynamics, or what is aerodynamics first. Okay, aerodynamics is the study, okay, or the science or engineering that studies the contact between air and a solid body. So now this solid body can be anything, and the train, cars, buildings, bridges, or any other thing. So train aerodynamics is a study of the aerodynamic behavior of a train when it's moving in an open air or in an enclosed surface. This can be tunnels or any other enclosed surfaces. Okay, so computational train aerodynamics involves the application of computer simulation and computational fluid dynamics techniques to analyze the airflow around trains. So we want to analyze how do these airflow affect this train, affect the train itself, and also the surrounding, the environment that this train is being operated. So it allows engineers to study the complex aerodynamic phenomena that occur during train operation. Okay, so we know that air is so complex. The turbulence of air is very, very complex. So this study tries to make us analyze the complexity of these flow in order to make an improvement on the train design or on the environment, maybe environmental structures such as maybe the bridges or the houses that are close to the railway. So by using numerical method, we can predict the forces, which are the aerodynamic forces, which include the drag force, the lift force, and the side force. Okay, and then we can also analyze the pressure, the impact, the pressure of air on the train or on the environmental buildings, which are either the buildings or the other structures, and other aerodynamic characteristics to optimize the train design. So the main essence of studying the computational train aerodynamics is in order to analyze, okay, to understand the aerodynamics of the train and its surrounding so as to provide a method of optimization, design optimization. So how are we going to perform this? How can we go about doing this? Okay. So here we talk about the methodology. So operations for train CFD analysis, how to conduct this train CFD analysis. First, we'll need to design the train itself, right? The computer-aided design of the train, which is the CAD design, right? So apart from that, we are going to also design the computational domain. This computational domain is just like the wind tunnel. So I don't know if any of you know or have ever seen wind tunnel. A wind tunnel is a study environment. It's an environment used to study the aerodynamic performance of vehicles. They can include the train, cars, and any other plane, and so on and so forth. So we try to replicate the computational domain. Okay, so this, as you can see in this picture, this is the computational domain. Sorry. So this is the computational domain here, as you can see in this picture. And this is the train model. And apart from that, we are going to design a body of inference. Okay, this body of inference help us to give different mesh sizes on different parts of the train or of the computational domain. Let's see. Okay, so first we will need to design the train model, the computational domain, and the body of inference. That's number one. Then number two, we are going to generate the computational mesh. So these computational mesh, what is a mesh? Mesh is the process of discretization. Discretization means that we will need to cut these computational environment. The train itself, because we are going to put the train inside the computational domain, the body of inference and the flow inside the computational domain, so as to provide a reduced computational power in each of the mesh. So in each of the cell, we are going to compute the aerodynamic properties, okay, using some computational formulas, such as the Reynolds average Navier-Stokes equation, or the other method, which are either unsteady methods. So we have two, as we know in our secondary school, we studied the steady state simulation and the unsteady state flow, steady state flow and the unsteady state flow, or the turbulence flow. So here also, we are going to have these two methods in solving the train, in studying the aerodynamic performance of the train. So first, number two, we are going to generate the computational mesh. And this, as you can see here, is the computational is the mesh generated on the train surface, and this is a projection around the bogey region, and this is showing the effect of the body of inference here. Okay, it's showing the effect of the body of inference. So we generate smaller meshes around the train, and then we increase the sizes of the mesh away from the train body a little bit away, which I call the coarse refinement box. I have the fine refinement box, and also we now allow the other parts of the computational domain to be like that. So number three is to conduct the numerical simulation. Okay, so we have also, since we have already generated the mesh, the next step is to conduct the numerical simulation itself, to allow the computer to simulate and provide us with the necessary data to analyze the aerodynamic properties of the high-speed train, or of the train. Then after that, we are going to see our results, right? To get our data after the simulation, we are going to generate data, which we are going to use tools for visualization to visualize this result. Be it the pressure forces, the flow, the velocity around the train, or the aerodynamic forces, either the drag force, the lift force, or the side force. Then in the first step, and the fifth step, is to analyze the data. These can be numerical data. These data are analyzed using other software such as Excel, MATLAB, or Origin, any other data analytic software. So what are the numerical tools that we need to perform these operations? So here I discuss about the numerical tools and their uses. Number one is the ANSYS space claim, or rhinoceros. This is used for train modeling or geometric design. So we can use either space claim or rhinoceros to model the train, or to provide some geometric add-ons on the train so as to study the aerodynamic performance. The second tool is the ANSYS meshing package. This is used to generate the computational mesh. So this meshing package, we have also other ones such as the ICEM, we have the Gambit, and other tools that you can use. But in this session, we are going to use the ANSYS meshing package. Then number three is the ANSYS Fluent. The ANSYS Fluent is used to compute the simulation, to perform the simulation, to conduct the numerical simulation, so as to provide us with data that we can use to analyze the aerodynamic performance of the high-speed train. The first one is the tool for visualization. These can be either insights or tech plots. Okay, these are also other softwares that we can use to visualize our result after simulation. And in number 5, the data analytic tools, which include the Excel, the MATLAB, and Origin. So now, case study. So here we are going to demonstrate the practical application and the benefit of computational train aerodynamics in real-world scenario. How to conduct this? Why do we even need to conduct computational train aerodynamics? Computational processes are carried out so as to reduce costs. That is the main essence. If we are going to have a real-time result, a good result, so we must have to conduct an experiment. An experiment provides us with the real-life result, the main result, the original result, okay, the good result. But the computational, because we are going to design it ourselves, and we are going to simulate it ourselves, and we are going to analyze the data ourselves. So we are going to reduce costs. In experiment, we are going to need to buy everything. We are going to provide a lot of energy and resources that can cost a lot of money. So that's why we need to do computational processes. In this case, computational train aerodynamics. Train is a very complex vehicle, very big vehicle. So to carry out an experiment, you need a lot of money, most especially the full-scale experiment. Other experimental methods also include the reduced scale experiment, which include the wind tunnel experiment and the moving scale or moving model experiment, which we know if you are in this school, we know that as you come to the school, they will take you to a tour on the different laboratories. So one of the laboratories they are going to take you to is a moving or dynamic test model rig at the High Speed Research Center there. So let's look at the practice, or let's look at how these processes are performed. So the first step, I say we are going to generate our model. Please, can you see my screen?
Yes, we can see it.
Yeah. So this is the high-speed train model, right? So this is the model we are going to use to conduct this study. So in real sense, we do not generate this model ourselves. If you want to get this model, you can either go to because this is an ICE high-speed train. It's a German train. So you can go to their site and you can download this model. This is also similar to other train models such as CRH and the TGV and other models. You can get them online to use them. What you need to do is to know how to model it, how to put your add-ons, how to put to add some designs that can improve the aerodynamic performance of these trains. Okay, so this is the train model we are going to use to conduct this study. Then the other geometry is the computational domain. This is the computational domain that we are going to use. Though we are not going to use this because of simplicity. We are going to use one without without track, okay, so that we can easily generate our mesh. And the other is the BOI, which is the body of inference. So these we are going, is just a box, depending on how you want to generate a mesh. So this smaller box here will generate smaller meshes around this area, around the area it covers. Then followed by this bigger one. So if you want to add more boxes, you can add more body of inference. You can add more boxes. Okay. So for people who want to conduct this study, after you get your model, you will need to name various parts of the trained model. So you see, this is the structural name, okay? But you have to group it because the software you need to get the data from each part of the train. So let's say, for example, I want to get the data from the buggy itself. What is the aerodynamic drag of the buggy? So I'll need to first name it as the buggy so that when I come to get the data, I can easily export the data for the buggy itself. So I will just highlight the part I want to name. Then I will now press Control G. Control G. Okay, it's going to tell you that yeah, say group one creator. So you can change the name as you wish. Okay, buggy one. Okay, but I have already make a name. I've already named all the various parts that I want to collect data from. So you see, this is buggy one, buggy two. So this is various parts of the train that I want to collect these data. Okay, I've already named them. So to name these parts, you are going to what do you call it? You get the parts and then you press Ctrl G, then you rename it. Then after everything, you can save. You can save either save or save as just by you want to give it a name. Okay, then you can now use it. Also, the same thing for the computational domain. Okay, so because for the computational domain, we have to name various parts that, okay, these parts I want it to be the velocity inlet. This is the parts I want to my flow, my air to pass. So I'll now name this thing, this part as an inlet. Then here is our outlet. So if the air is going to pass through this side, it should come outside from this side. Okay, it should come out from this side. Then here I can just name them as either front or back, and then here also back. Then this is the ground. This is the ground and also the top. And then these, if I want to name it, I give it a name as the track or the track bed. Anyhow. So also for this, I've already named it for various parts. So what you just need to remember is that for you to name, you highlight the face and then you press Ctrl G. Then you can give it the name that you want to give it. So after everything, you save. The same thing with the BOI. However, for the BOI, since we don't want to name various parts, what I need to do is just to highlight the various side of the boxes, and then I'll give it a single name. Okay, just like this. You have the fine. So here I want to get a finer mesh, and then we have the coarse. Here I want to get a coarser mesh, right? So that's why I named this part like this. So these are the various parts of the various component that we need to conduct this aerodynamic analysis or computational train aerodynamic analysis. So after that, I will now need to export this geometric model to my meshing software, right? So because if you remember, the first step is to create the model, the computational domain, and the BUI. So this is my model, this is my computational domain, and this is my BUI. And I have already discussed on how to go about grouping them or naming the various parts of these geometries. So I will go to my the meshing software. So this is my meshing software. So if I want to open, because for this is Linux software, Linux system. So I will need to open a new terminal, and I will now type Fluent, right? So the version I want is 2.1. I'll enter. So I'll select, do I want to mesh or I want to perform a solution? So I want to conduct a mesh. So I will now click on mesh, then I'll start. So it's going to open the meshing package of the ANSYS Fluent. Yeah. So this is the H opening. Okay. So it's going to take a little while to open because when running a new program, you have to be patient. So it has opened. Okay, here you can just go on to press OK. So I'm going to import my various models. So I come to File, right click on File, then come to Import, enter CAD. Okay, so it's going to open this window here. So you now come to these three dots. Okay, press on these three dots. So it's going to open your directory where you save the file. So you're going to the folder you save the file. Okay, so this is my BUI, which is body of inference. This is my computational domain, and this is my model. So I'm going to import each of these components into the software. So here I'll first click on the train, then I'll press OK. Okay, then I will see here you have the units. So you are going to maintain it. For here in this case, we maintain it as millimeter. Okay, millimeter. Then we have here scintillation. Here, tessellation, sorry. Here we can either choose to import it as a faceting or a surface mesh. Okay, we are going to see the difference between these two options. Okay, for surface mesh, it's just that we are going to import it as a surface mesh, not a volume mesh. So we are going to see the difference between a volume mesh and a surface mesh. What we need to generate, the mesh we need to generate is a volume mesh. Okay, not a surface mesh. A surface mesh is just like mapping. Okay, we are going to map the mesh or the parameter of the mesh we created on the surface of the geometry you want to mesh. So that is a surface mesh. So, but first we are going to maintain our faceting or the CAD's faceting, just to import only the geometry into the software. So we import. Okay, so done. It's done importing the train model. So I'm going to also go and import. So here, don't forget, you are going to see the first time I import, and you not click on this option, this append. This append helps you to keep the former one you imported. So you are going to press append, then the train model you first imported is going to stay. It's not going to disappear. If you do not press this append, it's going to disappear, and then you are just only going to import the new geometry that you imported. So we are going to press append. So I will append, then I will go, and then I will import the computational domain. Okay, then I'll import. So it's done importing the computational domain. So also I will go and import the BUI, that's the body of inference, which is this. Okay, import. So all I've imported are my three components that I needed to perform this meshing. So, okay, the difference between faceting. Somebody asked a question here. I can see from the chart window. The difference between faceting, okay, and surface mesh is that for surface mesh, we are going to faceting give us a window or an environment to create what we call the size field, right? The size field is just like you put in because ANSYS Fluent meshing is an automatic meshing. So you are not going to generate this mesh yourself, okay? You are going to input numbers, values on various parts of the train that you have already grouped, you have already named. Okay, so I want this mesh size to be equal to 1 millimeter. I want this mesh size to be equal to 0.5 millimeter. So you are faceting helps you to put these values first and then save it. Then you will now need to import the surface mesh using these saved size field that you have created from the faceting option. I don't know if you understand. So let's see it practically here. So after I've already imported my geometry, you see, this is the geometry object that you have imported. So here, you see, the system try to divide it. Okay, so this the coarse part of my BUI, which is the body of inference. This is my fine part. Okay, don't forget that we have a fine and coarse. This is my fine part. So you see, this is the coarse and this is the fine part. And this is the IC3. This is the model, the train model. So if I want to view it, I can also right click and then press on drop. Okay, then it's going to show me my train. So this is the train. So if I want to turn like I want to span, okay, I want to spin, sorry, I will press on the middle button of my mouse and then I'll move it. So it's going to, if I want to zoom, I can now either this thing, scroll it, either A, out or in, okay? So this is a train model and this is a computational domain. So if I want to view it, I'll view it. So this is the computational domain, okay? Okay. Also, these are the computational, the body of inference. I can also view them. Okay, so this is the coarse. Okay, and also this is the fine, as you can see here. So after I have already imported, I will go to model. Okay, here, this model here. I'll right click and I'll go to sizing. So here I want to impute these values that I already mentioned earlier. Okay, and I'll save them. So I will come to sizing and I'll go to scoped. I'll click on scoped. It's going to show me this window. So here I'm going to create my scope sizes, okay, by imputing values. And then these values are going to be create the surface mesh that the earlier questioner asked. Okay, so for the sizing, we have the global scope sizing. So the global scope sizing try to gives you a range, okay? What should be the minimum size of mesh that I will generate in all my computational domain, either the train inside it for the train body or inside the computational domain, what should be the minimum size? What should be the maximum size? If there should be any growth, what should be the growth ratio? Okay, the rate of growth, okay, between a smaller size and a bigger one. Okay, so this is the global scope sizing, as you can see. Then this is the local scope sizing. This local scope sizing gives you the liberty to say, okay, for this part, I want this part to have a minimum of this and a maximum of this. So this is going to give you a minimum local globe size, which is, for example, if I take the bogey only. Okay, I want the bogey, the side of the mesh in the bogey to be, the minimum should be 0.05, and the maximum should not pass maybe 0.06. Okay, so I've already specified as local scope sizing. Okay, this type helps you to give what type of mesh do you want to generate here. Okay, so here, if you click here, we have different options. We have curvature. This is applied when the parts of the train or part of the geometry have curves. So you apply curvature. Okay, you apply curvature. Then we have proximity. So this proximity helps you to give a certain size for the mesh. So it's going to maintain this size. For example, if you click on proximity, it's going to now give you option to say, okay, in each gap, let's see here, in each gap, how many cells should I put? 3 cells or 4 cells? You are going to specify the number of cells you want in each part. So here we normally use it when we want to mesh the what's it called, the track of the train, because you know on the rail, you know, is very small, the rail itself. Okay, so you want, okay, I want 4 cells on the rail. Okay, so just 4 cells on a portion of the rail, small portion, should not pass 4 cells or 5 cells, depending on what you specify. So for the train body itself and the bogey, since we have a lot of curves there, we are going to use curvature. Okay, other options include the mesh, the soft. So for this soft, we are going to it's going to be a kind of it's a kind of a mesh type that we use on the BOI. Okay, sorry, on the computational domain. Okay, then for the BOI, this is body of inference. We are going to say, okay, this is not actually a body that we are going to use in the numerical simulation, but it's a body of inference that tries to influence the mesh around the area it covers. Okay, so it's not going to affect, the mesh is not going to be on the body of inference, but in the area it covers. I don't know if you understand. So for hard tries to make the mesh there to be very small. And for these, when we conduct the numerical simulation, you're going to take a lot of time, though the accuracy is very, very good. Okay, so curvature. So curvature is what we are going to use for the train itself. Okay, train itself, which include the bogey part, the train surface, the carriage gap, and other parts of the train. Then the body of inference, we know, okay, we're going to use for the body of inference, which is either the fine or the coarse. Then the soft is what we are going to use for the computational domain. So apart from that, we have the growth rate. Okay, so I discussed about this growth rate earlier here when I talk about the global size. Okay, so it's from one mesh to another. What should be the rate of growth? Okay, you can specify either 1.2. Some in most cases we use 1.2. So, but you can also use 1.1 and maybe 1.3. It's okay. Then the normal angle. Okay, What should be there? Just like the normal angle or between for example, when you have a curvature, what should be the angle between maybe the edge of one cell and the other cell? So here you also need to specify. Then we have here scope 2. Here you see we have object face and edges. So here is going to any option you choose here is going to help you to show the names that you have already created earlier. So do you want to see the faces because you already name the faces, or do you want to see the face zone label, or the object faces itself, or the object edges, or the face zone, or the edge zone? Just anyhow you want. But in most cases, we normally label the face zone. We will use this face zone label because that is the option that the space claim naming try to use this one. So when we select this option, okay, it's going to open another window, which is this. So object type, geometry, okay. You're going to select geometry because that's what we was it imported, geometry, not mesh. So here we can select the object here, but we don't use that. We come to this part, we select the various part we have already named. So we are named the buggy, that's buggy 1, buggy 2, buggy 3, and so on and so forth. The car, okay, the computational domain, which we name as either back, that's the various parts, which is back, the front, the down, the inlet, the outlet, and so on and so forth. Okay, or the train surface, which is the buggy 1, and so on and so forth. Okay, so this we are going to do for each and every part of the train. Okay, so for example, I want my global size to be the minimum, to not exceed 0.015. Okay, and the maximum should be 6. Okay, and then the growth rate is 1.2. So after I've already applied it, put these values, I use apply. So it's going to apply for every scope size on different parts I'm going to create subsequently. So I come to local global sizing. So here I name, I want to create global, the local sizing for the car body, right? The car body. So I name it. The car body, as I said earlier, we're going to use curvature. So, okay, curvature. So for the car body, the minimum local scope size, I want to use 0.03, for example. Okay, and the maximum shall not exceed, let me use 0.035. And the maximum should not exceed 0.4, 0.04, 0.04. Okay, so the growth rate is 1.2, and the normal angle, I leave it like this as 18. And then I'll come to this, since this one is okay. Face zone level, that's what the option you're going to use. And I'll come to label selection. I will now select only the car body, okay? The car surface, which is car 1, car 2, car 3, okay. After that, I will press this create. So it's going to create here. So this is car body. Okay. So the same way I'm going to also do for the buggies. So I just come here and name the buggies. So the buggy should not exceed maybe 0.3 and then 0.0335. because I need smaller meshes on the buggy surface. Okay, the type should be the same, which is curvature, because there are a lot of curves on the geometry of the buggy. So here I'll come here and I'll select all the buggies. Okay, buggy 1, 2, 3 up to 6. I'll press OK, and I'll now come here and then create. So this is the buggies. So the next is the computational domain, right? So I'll come to, I just click, name it as domain. Okay, here I said we are going to use softs. Okay, softs. So I'm going to give an for here, when you click on soft, it's going to just only give you option to put the maximum, no minimum. So for this, I'm going to just use 4, because the maximum mesh size in the here, there's the global scope size is 6, so I can use any this thing I want to use. So for here, I use 4. So I'll come here and I'll select all the parts of the computational domain, which is back, the down, the front, the inlet, outlets, and up. Then I'll press OK. Then I'll create. Okay, so it has created the computational domain. Then the next is to create the BOI for fine, right? For fine. So here I have different. Let me first do for coarse. So I'll name it as coarse. So here I told you that we are going to use BOI option. So also for BOI, you see, it gives you only option to put the maximum. For this maximum, for the coarse, let me use maybe 0.5 or 0.65. So I will come to this place and I will select the coarse. Here, coarse. Okay, and I'll create. Right. Then also the remaining ones are the fine. So I'll come to this one. I'll press fine. Okay. So, but in these my option, I have different fines, if you can see, because these parts is actually train model is the train model I use in my second paper, which is the study of the effect of intercarriage gap configuration. So because I want to study the intercarriage gap, I also put a mesh, that's a BOI, so that to define the mesh around the intercarriage gap to be smaller there, because that's my area of concentration, okay, area of study. So I want the mesh there defined so that it can have a good result there. Okay, so because the finer your mesh, the better your result. Okay, so that's why I use these fine tool in that area. So that means my my BUI is not just 2, it's 3. Okay, that's the bigger one, that's the coarse, the smaller one, that's the fine, and the more smaller one around just the intercarriage gap, which is the fine 2 that I name it here. So I'm going to do for the fine 2. So for the fine first, which here I'm going to give it maybe 0.4 as the maximum. So just fine here, right? First, okay, and I'll create. Then the second is fine 2. Fine 2, I'll come to this place. I'll now choose fine 2. Okay, then create. So these are the various scope sizes that I've created for various parts of the tree, right? So after doing this, I'll click on this plus. I saw this this thing here, this option here. I'll click on this. It's going to highlight all the parts, and I'll come first. I will need to write, okay, because I don't want to lose these data that I've generated. I don't want to lose this scope size, so I'll go to write it. So I just give it name as CS or scope size. Okay, okay. Press OK. So it's going to see here. It shows that it has successfully written the file. And after that, I'm going to compute. Okay, compute. So this compute is going to compute these parameters that I impute. So after that, after computing, you can close, and then you can go to this file. Click on file, then click on write, then write size field. So we are going to, what we do here is to create the scope size. After computing, we can now write the size field. This size field is going to be the one that we are going to use to generate the surface mesh. All right, so it's just like an option for mapping. Okay, I want to map, I want to mesh this part to be this, this, and this, okay? So I've already created that. So I'm going to come to this place, size field. So you come to file, you come to write, and you see size field, and you now click on size field. So after clicking, it's going to show you this window. Then you can name it, okay? What name do you want to give it? Maybe size field, okay? ANSYS, that's what I did. Then we now press OK. It's going to write the size field. So let's finish writing the size field like this. So the next thing we are going to do, so we are done creating the scope size or the size field. So we can now go to option. Sorry, the file here. We are going to import again, but in this part, or in this case, we're going to import using surface mesh, right? So we come to file, you come to import, come to CAD, right? So don't forget, in this case, we don't want this geometry anymore. So we are going to remove this append. Okay, we remove the append. So we are going to import the various files. So we come to these three dots. First, you import the BUI. The BUI. So for the BUI option, we are going to maintain this faceting. As you remember what I said earlier, that we are not interested in meshing the BUI, right? We are only interested, what we want the BUI to do is to create environment, okay, to create an area for us to mesh the flow or the flow in that area. Okay, so I want a finer mesh in this small area, then a coarser mesh in this bigger area. So we don't need to use it to import it as a surface mesh. So we are going to maintain the option of faceting. So after clicking menu, you maintain the faceting, then you import by removing this append, because we are going to delete all other components here. So come to import. So it's going to tell you that any unsafe data will be lost. Do you want to proceed? You say yes. Okay. So you see here, it's remove the other components and then imports only the BUI to the software. So we come again, we import the trim model. So in this case, we are going to append because we don't want our BUI to lose. So we append, and then we come to these three dots, we select the trim model, and in this case, we are going to select the surface mesh, okay? Because we want to map the mesh on the train surface. Okay, we come to CFD visiting. It's going to show us this. So, okay, it's going to open this thing. So this option gives you a room to say, okay, I want to do the scope size, also the size field here. Okay, so you can either do the size field here or you do it earlier as we did. So if you don't want to, since we have already done it earlier, you're going to click on this use size field file. So because we have already generated the file, so we are going to click on this. Okay, so it's going to show you this. Please make sure to use the correct size field file considering the length units specified. You now press OK. So here we are going to click on these three dots. Okay, then we are going to choose the size field that we have already created. Right? We have already created. So I'm going to choose the size field, which is this. Okay, but this is the one that we created. The reason why I'm not going to use it because I just use my instinct in imputing the values. So it may be correct to create a good mesh, or it may not be correct. Let me use it. Okay, then after using it, I will now going to import. So it's going to import the various the train model. So here is going to take a little time to do this. Okay, but I have earlier done that. So you are going to get something like this. Sorry. Yes. So you're going to get something like this. So this is the first import. Okay, that's importing the train model, right? As surface mesh. So it's going to put the object on this mesh object instead of this geometric object. So it's going to place it here. Also, I imported the computational domain, which is this, and I'm using the same option as the earlier import, which is using the surface mesh option. Okay, so after this, what I'm going to do is to check the quality of my mesh, okay, or the fidelity of my surface meshing. Okay, so what I'm going to do is to right click on the train first, and I will come to diagnostics. Okay, so I want to check the connectivity and quality. So I come to connectivity and quality. Okay, so these are various repair options. Okay, these help us to repair our mesh if it has any problems. Okay, that's the surface mesh if it has any problem. If the surface mesh has any problem, we cannot generate the volume mesh. So I think this is the first time I'm mentioning volume mesh. Volume mesh is our main target, not the surface mesh. Okay, we want to, yes, we wrote two files earlier, right? What we need, just yes. Earlier we wrote the size, the scope size. This scope size help us to keep the options. Like for example, now, if for example anything happened, or I want to generate the mesh again, I don't need to come again and say I want to impute the various numbers I have inputted. Okay, what I'll just need to do is to read it. Okay, instead of this thing, I'll just come here and read scope size, which is this. Right, it's going to give me everything I need, all the scope size that I've already created for the various parts. So it's not that we need it to generate the mesh. What we need is the size field, which is this option, this one, this size field. That is what we need to create the surface mesh. That's why we now save this, okay, which is SF. Okay, that's why we save this, because we are going to use it as an option here. So when we come to this place, import, okay, is here, right? As I said earlier, also we have already imported the train model. So we are going to also import the computational domain, which is this. So you see, the first time we use this option, but in this case, we are going to use this option, which is the surface mesh, okay, the CFD surface mesh. So you see, this option, use size field file, okay? The size field file is going to be generated when we compute the scope size. So we compute the scope size, and then we now go on to write the size field, just like this. So after we compute the scope size, we come to here, a file, we come to write, and we come to here, write size field. So that's why that's what we did earlier. This and now name it SF, and then we save. Okay, we write. That's why that's what we did, because yeah. So that's why we need these two to write these two files. So we are going to import the computational domain. So computational domain. So we use the same option as what we used earlier to import the train model. So import. So as I was saying earlier, I've already done that in this thing. So this is it. So we import the various, that's the computational domain is going to be on the geometry objects, and also and the mesh objects. We are going to have the train and the computational domain, right? Because this BOI is going to be here because we said we don't want the BOI to be meshed. What we want it to do is to mesh only the environment it covers, the area it covers, inside the area, right? But we want to mesh the train model and the computational domain. That's why we did this. So after that, I said we are going to check the fidelity or the quality of our surface mesh. So I will come to the train. I'll right click. It's going to show me this, and I'll come to diagnostics. So diagnostics is going to I'm going to see these two options. I will now come to this connectivity and quality. I will click it. So here is help me this window. What it is that I can use the various these tools. These are tools actually to perform various operations to improve my mesh, my surface mesh. Okay, these are tools. If I have three faces, or I have multiple faces, or if I have faces that are intersecting, okay, duplicate faces, and so on and so forth, leak, okay, and so on. I can use them to what's it called? Amend my mesh. So what I'm going to do first, since I don't know what is even wrong with my mesh first, I'm going to click on this summary. It's going to give me a summary of the various problems I'm having. Okay, so you can see here, this is the summary here. So for free faces, I'm having 0 free faces. I don't have any problem with free faces. Okay, I don't have free faces. But for multiple faces, I have a lot of multiple faces. About 1,410. Right? Then for duplicate faces, I don't have any duplicate faces. Okay, for skewed faces, also 0. Maximum skewed, this is the criteria we use to check the quality of our mesh, of our surface mesh. So the smaller this value is, the better our mesh. So, but when we have 1, that means our surface mesh is not good. We must have to improve it. And these high value may be due to the geometry. If maybe your geometry have a lot of problems, the connections, the edges has problems, you're going to get a lot of, the number is going to be very, very high here. Okay, so when doing this mesh, we should try to make sure that our model, okay, the model, that's a train model, is very, very good. The connectivity good. The edges are very tight and so on and so forth. Okay, the faces, no free faces. Okay, then we are going to get a very small option here. Okay, then we are going to do small repair when we come to this repair option here. We're going to do just a little work. Okay, then we have all faces that's all faces that it can identify. Okay, then we have phase zones, 11 phase zone. It doesn't matter actually. So this one and this option is not a thing that you need to check. What you need to check is this one, which is the maximum skewness, the free faces, the multiple faces, the duplicate faces. Okay, you should make sure that this one is 0, the multiple faces is 0, the duplicate is also 0. Okay, this is what you are going to make sure. So here we see that we have multiple faces. Okay, we are not going to check which parts has this too much multiple faces. Why do we have this? Okay, the acceptable range of the skewness, somebody asked, is that just like quality, right, is between 0 to 1. So it simply means if you have 0, a mesh is very perfect, but we cannot have something very perfect. Okay, so it simply means the lower the better, the lower the better. So if you have 1, it's poor, very, very poor. If you have 0.5, it's good. Okay, very good. If you have 0.4, it's very, very good. If you have 0.3, excellent, it's very good. If you have 0.7, it's fairly good. Have 0.8, you need to, it's okay, but you need to improve it. Okay. So let's work on these multiple phase. Okay, we are not going to, okay, we'll go to this. Since we have multiple phases, we click on multiple phases and we mark. We want to see them. Okay, come to mark. We press on mark. So it's going to show us the number of multiple phases here. Okay. Oh, I think it's still working. Okay, we're not able to say it. Okay. So this the diagnostic tool was unable to tell us or show us the multiple phase. But I know what is the reason for this. So the reason for this is actually because I have, now if I want to show the various parts of the train. Okay, so you can click on this plus. If you click on this plus, it's going to show you another listing, which is going to show you the phase zone here, the volumetric regions and the cell region. So you click on this plus. Also is going to show you the various parts that you've already named. So I want to see the car 1, which is just the first car. So yeah, so I draw it here. So you see, this is the reason for the multiple phases. Please, you cannot have a hidden face. Okay, for example, I want to also see car 2. Okay, so I come to this, I click and come to draw option. I will now press on add. Okay, that's add geometry. Yeah, so this is it. Let's go into add. So you see, if you can see that face that I earlier showed, the face in the carriage gap is going to be a face that cannot be meshed. Okay, because we cannot find the aerodynamic forces on that face because it's already closed. What is the essence of that face? So it's going to be a redundant face. So the system is going to see it as an error, okay, as a cause for error. Then the measure is not going to be generated at first. Okay, so we need to delete that face. So I will need to delete that face. So I will go to only show this, and I'll click on the face. Okay, just click on the face. That's left click, right? Yeah, let's click on the face. So it's going to show you this. This is delete. Okay, you will not delete it. So deleted. So let me see for other cars. Do I have this face? So you see, here is there's no face here. Oh, I'm having it here. Okay, so left click, I'll delete. Okay, it's gone. Also, let me see car 3. Okay, for car 3, this face is not here. So it's okay. So what I will do next, to see, since now it's going to be a free face, okay? This edge is going to be a free edge. So what I'm going to do is to stitch it, okay? To come to, I'm going to click on the train model. As I click on the train model, I come to the diagnostics, connectivity and quality. I come to free face, okay? Free, okay? Because it's going to create free faces there. So I'll come to free. I'll come to stitch because I want to stitch them. I want to stitch the cars. Okay, between car 1, car 2, and car 3. Let them be stitched. Let them be one component also. So I'll come to stitch. I will now click on apply for all. Okay, so you see here is going to show you that it's stitching car 1, car 2, car 3, and so on and so forth. So it's done. It's done. Though it's going to show you that see here it shows you that it's only stitch. It does not stitch anything. So it simply means that this thing is okay. So when I come to summary again to see what my mesh is, how my mesh is, if I have other problems, so you see I've solved this problem. Okay, so no multiple faces again because I've already deleted those redundant faces. No multiple face, no free face, and no duplicate face. Okay, and the skewness, the maximum skewness is okay because it's very small. It's 0.5758. It's okay. We can continue. Okay. So I said we don't need to mind this and this. So we close this window. So the next thing is to merge the training and the computational domain. Let's merge it. So we come to this. Shall we now merge? Okay, when you are going to select this and then press Control and select this, then you now right click. Okay, you come to merge. You now click on merge objects. So it's going to show you this this window. So you will have to rename it. Okay, you give its name called fluid. Okay, then you merge. So it's going to merge into one component, which is fluid. Okay, so after merging, I am going to, okay, it's going to be like this. So I'm going to click on these plus. Okay, when I click on these other plus, it's going to show me the various parts that I already merged. Okay, that's the buggy, the part of the computational domain, which is the inlet, the outlet, the up and down, and so on. Okay, so but I don't need it to open it, so I just close it. So what I want to do is to right click on these volumetric regions because I want to divide these regions. Okay, what is solid and what should be fluid. Okay, inside the computational domain, it's supposed to be fluid, it's supposed to be air, right? Then the train itself, it should be a solid body. So I'm going to separate them. We match them, but we do not separate them. Okay, so the system is going to identify if this is a solid or this is a fluid region. So I'm going to right click and I'll come to compute. It's going, okay, and I'll compute. So it's going to compute, and then it's going to divide the various parts. So you see, it has already finished computing. You see, done. So it's going to, after computing, it's going to show you this plus sign. So you click on the plus sign. So you see, we have the train and the computational domain. So the train is solid. This is solid option, okay? So we don't need to change for the train. We come to computational domain, and then we're going to change it to be a fluid region, right? So we right click, and then we see change type, right? It's solid before. See, it's solid before. We're now going to change it to fluid. So you see, it's going to change. You see, instead of this icon here, is just change to another type of icon here, just this. So after that, I've already changed the what's it called, the type, okay, of the zones or regions. So after that, I'm going to right click on this cell zone. So this is now the time I'm going to create the volume mesh, right? So I'm going to right click on this. It's going to show me this, and I'll come to auto mesh. It's going to show me this option. I don't want to keep any cell, solid cells, and so I'm going to remove this option. Okay. So objects, the name that I already give it is fluid. So fluid. So boundary layer mesh. So the boundary layer is very, very important. Okay, important, most especially in solving that's the boundary layer mesh, in solving the fluid close to the train surface, because we are going to see various method of solutions. Okay, because to solve the aerodynamic properties, you need to use a lot of different methods. If there are a lot of methods, so it's either you want to assume that the flow is a steady flow or it's an unsteady flow. That means we have a lot of turbulence. I want to say, okay, it's a steady flow. So we have steady state simulation and we have the unsteady state simulation. So this boundary layer is an option. There is a criteria. It's for to use some computational models, you must have a certain number of boundary layer mesh that can create a certain y plus value. I don't know. Maybe I'm going too deep here. Now, y plus value is a numerical, what's it called, indicator used to know the effect of boundary layer on the train surface. Okay, so the y plus value try to give us an idea on how very close we can solve the flow close to the train surface. How accurate can we solve it? Okay, so this is very important. So what we are going to do here is that we are going to create a prism. Okay, so here we are going to click on this side. So we are going to choose the scope. Show it here. Okay, then we're going to set. We're going to press on this set. So it's going to show us another window here. So here we are going to now attach how many layers do we need on the surface of various parts of the train. The bogie, okay, the train surface, at the bottom of the computational domain, okay, and at the computational domain, how many layers, how many cells, how many layers, okay, do we want to put there? Okay, So for example, for the car, which is the car body, okay, the various cars. So we are going to maintain this offset method. It's either we use uniform aspect ratio or last aspect ratio. We normally use this aspect ratio. So for the train surface, normally to get a smaller y plus value, we are going to use 35, and the and the um and the number of layers, we are going to use 20. Okay, 20 layers. Okay, these options you can also see them on various papers. Okay, if you read some papers, you see they will tell you, okay, we use so number of layers on the train surface, so our y plus value is equal to this. So it's very important. So I'm going to use 20 here for the train surface. So 20, so I'm here 35, and then here I'm coming here to choose the scope 2 what? Over here. Yeah. Okay, we select this option. Okay, then we click on this boundary scope here. It's going to show us the various parts. Then here we want to do for the train surface. So we click on the train surface care as car 1, car 2, car 3, then OK. Then we create. Right? Also, we do the same for the bogies. But for the bogies, because we have a lot of small places there, so we must have to reduce these values. So for the bogies, I'm going to use 25, and here should be 10. Right? That's the layers should be 10, because when you put more layers, there are small surfaces or small gaps, then the layers cannot be what's it call it created. So when I use small number of layers, then I'm okay. And I'll come to also this place and I'll choose all the bogies. Bogie 1, 2, 4, 5, 6. Then okay. Okay, right? And I'll create. So I've created for the bogies. Also, for the computational domain. Okay, for the computational domain, I call it domain. Right. Oh, I'm going to maintain the same option as the bogie. So I'm going to choose the various parts of the computational domain. Is the back, the down, the front, the inlet, the out, okay, and the top. Okay, and I create, right? So these are what I need to create the prism, the scope prism. So I'm going to click on this option here. Then I'm going to write, just as the earlier the person that asked question, why do I write? Because I don't want to do it again when I come back again. So I'm going to write, right? I'm going to write the file. So this is prism, okay? Prism, let me just save it as PR. So you're going to write. So you see, that's successfully written the file. So you maintain this and then you close this option. Okay, after closing, so we are done with this. Here, we maintain this option here, these pyramids. We maintain, just don't change anything. Then here we want to see, okay, what type of mesh do you want to generate? Do you want a tetrahedron mesh? Called as hexahedron mesh? You want a poly mesh? Or you want a hexa that's polyhex core, that's polyhexahedron kind of meshes. So For this, we're going to create a poly hex score. So we'll click on this. And we're okay. Now we come to these options. So here also we are going to click on this merge cell zones within region. Click on this option. So this is okay. Then we are going to apply. Click on apply. Okay, so it's okay. After that, we are going to click on mesh. So this is now the part that we are going to generate the what's it call it, the volume mesh. Okay, so click on mesh. So it's going to show you this question. Then you can just say yes. Just click on yes. Okay, this is it. So here we are generating the volume mesh. So here it's going to take a little time to generate the mesh itself automatically. Maybe like 5 minutes, 7 minutes, depending on your mesh options or sorry meshing parameters. So this is the various operations you are going to do when generating the computational mesh, right? So the first thing we need is to generate our various components, okay, which is the train model, the computational domain, and the body of inference. That's the geometry. Then the next is for us to generate the computational mesh. This is what we just did right now. And the computational mesh is the system is trying to mesh it, to mesh the various parts. When it is done, it's going to show you done. Okay. So to save time, I have already done that. Okay. So sorry, this is the not that, not that, not this, not this. Okay. Not this. So let's just wait. I think I did not import it to the listing. I can still import, but no problem. Let's wait for this to finish. It's going to finish.
Okay, thank you. So sorry, Malik.
Yeah.
Yeah, I don't know. Like, see, I noticed that like we've not finished with the methodology, talk less of going to the data analysis. I don't know if we can make this session into maybe next week we continue with the data analysis. Maybe
Oh,
today we just round up with the or do you plan
okay.
on finishing everything today?
No problem. We can wait if you want to us to do it in 2 sessions. If not, the
Yeah.
data analysis is actually a very simple thing. I think the first person I think that led you in the last session, right? He
Yeah.
discussed about data analytics and how to process data using various. He even introduced how to use Excel to process data. These are data. What we just need to do, what we do in data analysis is just to create graphs, right? To create graphs and analyze our data, okay, to see, to calculate the aerodynamic forces, okay,
No, I'm
the
just okay.
pressure
No, okay.
forces.
I understand. I understand.
Yeah.
I just thought of maybe like there's a special or maybe since you said
Yeah,
it's
no
simple,
problem. Yes,
so
let's
we
have it
can.
actually.
Okay,
We
okay,
can
okay.
have another session, maybe next week. We can have another session to um, carry out data analytics.
Yeah,
Or
maybe explain more on the simulation results if possible.
yeah.
Yeah.
That is, we can do that.
So maybe if you're almost done, or you can just elaborate more on the methodology so that
Yeah.
we won't just rush through the this methodology
Okay.
process.
Yeah.
Yeah.
Okay.
Okay.
Yeah. Okay. So, okay, so this is it. Our our mesh is finished. We are finished doing the generating the mesh. So if you want to see our generated mesh, we are going to see you're going to see it here. So you right click on this, you see draw all boundaries. Okay, so you click on draw all boundaries. So this is it. Okay. So I want to see the mesh, right? So I'm going to click on these face edges. So this is it. This is the mesh we generated. Mhm. So I want to see the train, right? So you can see the train. Mm. Yeah, so this is a train here inside the computational domain. Mhm. So you see, so we can also check the quality of our mesh. When you come to this place also, you come to summary. Okay, it's going to show you the mesh quality, right? Yeah, so this is it. This is the mesh quality. Okay, but it is okay. The mesh is okay. If it's not okay, it's not going to even generate the mesh. It's going to show you some errors. So this we are done generating our mesh. Okay, so we are going to write it. Saving it, right? So write, you come to file, you come to write, and you come to mesh. That's you want to save mesh. So we give it a name. So, okay, so it's going to save our mesh. This is going to take a little while, depending on the size of the cells. So for this one, we generated about 27.7 million meshes. I mean, a cell, sorry. This is the cell, the mesh, what's it called, the cell number. So it's 27,750,000, then 600, something like that. That's 17.7 million. That look, in paper, you just see 27.8 million cells. Because you're not going to write the other and just approximate. Okay. So it's going to take a little this thing. So after meshing, after saving, you're going to see it's where you save your this thing. So we are done doing mesh. Okay. So I have already done one, which is this one, the volume mesh. Okay. So to do the simulation, okay, we are going to move to simulation option, right? What we did in the first is to use the meshing option. So we're going to use now the solution option. Sorry. So we right click, we open new terminal, and we open Fluent 211, which is the version I'm using here. Enter. So you see, this is the option we used earlier. But now we want to do the simulation. So we use this option, which is solution, right? So here you can see you can write the number of machines, that's local machines you want to use. Okay, so we can use depending on the system. Okay, the computer, how many this thing are there, the processors did the computer have, and then you try to see how to manage these processors. Computer I'm using in the lab, this one that I'm using is about 120, right? Something like that. So I can use 64, I can use 96 also. So let me just maintain this option. So now I will start. So it's going to open the solution window. I'm going to take a little time because we're just launching a new program, so we have to be patient. Okay, so it's open. So here we just click OK. So we are going to import the mesh that we have generated, right? So we're going to read what? We read mesh. So this is the mesh. We're going to read. So it's going to read the mesh. So also here it's going to take a little time. We have to be patient. We have to be patient here. Also, it has to read the various parts of the train and the mesh, the cells, and so on. So here, the number of your cell number is going to also determine how fast it's going to read it. So if you have a lot of cells, so for me here, I'm having about 27 million, right? So if you're having 50 million, it's going to be much slower. If you're having 10 million, it's going to be fast, much faster than 27 million. So the number of cells matters in the time taken for simulation or time taken to read the mesh file. Yeah, so it's done. Okay. So here, I need to know my input parameters, right? What are the input parameters that I need to use in order to make this simulation? So here you must have to either meet your supervisor to give you an input parameter for new researchers, people who are new into it, right? So they have read some materials, but they do not understand it that much to say they want to make decision themselves. Okay, or you have to read standard, because we have standard various standards. Okay, just for the train we are using ICE3, which is a German train. So we are going to be using the EN standard or the European standard. So it's going to give you the various computational parameters that you can use to study the train aerodynamics of their own type of train. Okay, so this train that we are using is ICE3 high-speed train without what do you call it, track. And when you look at the standard for ICE3 high-speed train without track, okay, on stationary ground, the scale, they didn't use 1:1, that is the full scale high-speed train, right? They use 1:7 to conduct the experiment. So because you want to make sure that your result is good, your result is tallying with a standard, or your result is tallying with an experimental result. You don't want to get a result that is just only for yourself, only your own results. You want to get a result that is tallying with other researchers. So you must use the option first. Then after you use the option and then your result is good, you can now say, okay, my computational parameters that I use is okay, my mesh is okay, my result is good, then I can make modification. Then if I make geometric modification, I can now say, okay, I want to use the same computational parameters, okay, to simulate. Then I will now have a different, when I now have a different aerodynamic properties, nobody will question me, nobody will query me that my method is not good, because already I have validated my results using the same parameters as the standard. So in this train, we are using 1:7, right? So first you click on general, or it's going to just show you this. So you come to mesh, okay? You come to this scale. So you want to scale your this thing, your train. Okay, you come to scale mesh. You're going to click on this specific scale factor. Okay, after scaling, after pressing it, it's going to open this option. Then you are scaling it 1:7. So what is 1:7? That's 1/7, right? 0. What? 0.1 divided by 7. 0.1. Sorry, 0.14285857. Let me just use this. Okay, so this is going to be the same scale in X, Y, Z direction. So I'll now scale. Click on scale. Okay, so when it's done, these values are going to change. You see that. Then after that, I'm going to close. That is okay for scaling. Now, type of solver is very important. There are different types of solvers. Okay, we have the pressure base, okay, and density base. In most aerodynamic analysis, we use the pressure base solver because you need to couple the pressure and the velocity field. That's what they call coupling. Okay, so we use pressure base, so you don't need to change this option. Okay, also for this velocity formulation, you can use absolute or you can use relative. Anyone is okay, but normally we just maintain it as absolute. Yeah. Now, this one is very, very important. Time. Are you making a steady state simulation or unsteady state simulation? Are you assuming that the flow is steady or is unsteady? Depending on what you want to do, right? So you can choose steady states or transient. Transient is the same thing as unsteady, right? So it depends on what you want to do. Yeah, so we are doing steady state simulation because for steady state simulation, it's going to take you a little time, maybe 6 hours, 6 hours to maybe 7 hours, 8 hours, maximum 1 day, depending on your cell, number of cells, right? But for transient simulation, it's going to take a lot of time because now you are going to be you want to make sure that there is time factor there, right? From the Reynolds average number six equation, when you put the time factor there, then it becomes very difficult to solve. But when you remove the time factor there, then you are going to be assuming that the flow is steady. It doesn't change with time. Okay, but for transient, you assume that the flow characteristic changes with time. So in this our demonstration, we are going to maintain steady state simulation so that we are going to have our results. Then as our host suggested, next week we are going to now get our result, because if we perform the simulation, we cannot get the results right now. We must have to wait till when the data is analyzed or computed or simulated before we can get our results. So next week we can now analyze these results. So we maintain steady states. Then for this gravity, really we do not use to account for the gravity in this simulation. So that's it for this. So the next is models, right? For models, we want to select which type of model we want to use in simulating our flow. Okay. So as I said earlier, we have the steady state and the unsteady state simulation, right? So the same way we have different models to compute steady state and unsteady state simulation. So, but for this first, we are doing we are assuming that the flow is viscous flow. So we enter viscous here first. The models you see we have different models and they have different model constants, right? And under the models we also have other modifications for these models, okay, and options, right? So this is a very wide area that you can study, because different models have their different mathematical derivations and different ways that they come into play. So if you want to study this, you can go into the internet and study them one by one. Okay, Laminal, Almaraz, K epsilon, K omega, okay, and so on. Detached eddy simulation, large eddy simulation, and so on. For this, we are going to maintain using K omega. K omega is very important because it's a RANS method, that is a steady state simulation method, and is fairly accurate in predicting the forces on the train surface. Okay, so it's very important. So here, that's where the y plus value comes. If the y plus value is more than 1, okay, some researchers will tell you that the K omega model is not going to perform very well. So why do you use it if your y plus value is small? It's more than 1. Ideally, y plus value for K epsilon for K omega should be less than or equal to 1. But in real case, it's very difficult to get even 1. So that's why a range is allowed. Okay, you can get between 1 to 10. It's okay. It's okay when your result is having less variation with the experimental results, right? Maybe 0.5, maybe between 0 to maybe 10% is okay. That is when you compare your simulation result and experimental results. The difference, the variation, the deviation should not be 10%. Is okay for my group. Okay, so for the guys in my group, 10% our supervisor is going to accept. But more than 10%, you must have to do another simulation. But when you go to the internet, they will tell you up to 20%, up to 15%. It's okay. Okay. So here we are going to choose, there are different options. We have standard K omega model. We have this Gecko, we have BLS, we have SST K omega model. So we're going to use SST K omega, which is very good. So for this, we are not going to select this option, just leave it. So for options, we are going to use production limiter, which is okay. Then we press on OK. So this is it for computational model. Okay. You can also choose other models. Okay, K epsilon model is also good when you want to, when your main area of study is not the train itself, but the surrounding flow, especially when you are studying the wake flow, okay, or you are studying the slipstream, okay, slipstream. Slipstream is this air that is generated when around the train when the train is passing. Okay, so this is going to affect the structures close to the train or people standing by the rail. It's going to affect them. Okay, so it's very important to study the slipstream behavior. So also we have scale adaptive simulation, which is very good also. Also we have a study simulation and knowledge simulation. But these are used for unsteady state simulation. So note that. So for steady state simulation, you can only use K omega, K epsilon, and then they have different options. Okay, either standard or you have for K epsilon, you have standard, you have RNG, you have realizable. Then for K omega, you have standard, Gecko, BLS, and SSTQ omega. So for this demonstration, we say we are using SSTQ omega. Okay. So this is for model. So we now come, you don't need to do anything here in this material. Okay, just leave it. Also for cell zone, it's going to read the cell zone you have already, that name that you give it earlier in the mesh. Okay, don't forget we name it as fluid, so it's going to read as fluid. Okay, so then for boundary conditions is very important, right? Because in every simulation, you're going to do either solid state simulation or fluid, which is a fluid dynamics simulation. You are going to need to apply a boundary condition. So here, click on boundary condition, this plus, okay? We click on it, it's going to show us this option. We don't need to do anything in this internal, it's just on the wall. So for the back, we right click and we choose symmetry. These options are, you can get them in different papers, okay? They are going to tell you what they use. So for back, they will tell you, okay, we use symmetry. For front, we use symmetry, and so on. So for front also, I'm going to use symmetry. For up, I'm going to use symmetry. Then for the inlets, okay, I'm going to apply velocity. So I'm going to use velocity inlet. So for the velocity inlet, it's going to show me an option here, which is this window, to put the magnitude of velocity that I want to use. So here I'm going to not going to use this option. So there is velocity specification method. So you want to use is it magnitude normal to the boundary? So normally we use components of velocity components. Okay, in the x direction, that's what we use. Okay, the velocity on the x direction. So for here, I'm going to use 60 meters per second. 60 meters per second. Check my a lot of my papers. I use 60 meters per second. So for the turbulence, this thing, intensity and this thing, I'm going to use this option. I'm going to use intensity and scale length. That's turbulence intensity and turbulent length scale. So for turbulence intensity, this is also very, very important because it's we need to, I don't know, because studies have not been done. I don't know, maybe I did not read any study that talks about turbulence intensity and the magnitude, how it affects the simulation results. But it's one of our group member is going to do this in his thesis. So we await the result to see what's happened when you vary this option, this value. So normally what I use, because this thing is supposed to be not more than 0.5 in use. If you read some papers, you're going to get this. It's not supposed to be more than 0.5 for high-speed train. So, but now for me, what I do is to divide the length of the train, divide by the that's the length divided by the scale I use, right? So for high-speed train, we use 3 as the length of that's 3 meters as the length of the train. So note this, please. We use 3 meters as the length of the scale. That is the what's it called? The zoom length, 3 meters. So 3 divided by the scale, which is 7, I get 0.42875. Okay. Then for a turbulence length scale, sorry, not for these actually, for this. And for these, I use 0.5, which is the maximum. So now apply. Apply, then you close. Okay, that's for the inlet. For the outlet, I use pressure outlet. So normally we use pressure outlet for high-speed train. Okay. So we use pressure outlet with gauge pressure of 0. So what you are just going to change here is this option, which is intensity and length scale. Intensity and length scale. So you are going to use just the same value you used as the earlier, that's 0.5, and this, which is 0.42857. Then you apply. After applying, you close. So for the down, okay, which is the ground. For the ground, you can either leave it at a static ground. Let's say, for example, you want to simulate the train and assume that the train is on static ground, that's static ground or stationary ground, or you want to assume that the ground is moving, that is relatively to the train, because a wind tunnel, we know that the train is normally stationary. We are going to pass air, okay, over the train. But if you want to recreate what really happened during operation, we are going to use moving ground. So we are going to assume that, okay, the ground is moving relative to the train. So it's just like the train is moving, right? So let's use so you double click here, let's click here, and then you can change. So you see this option, wall motion, the stationary wall or moving wall. So we're going to use moving wall. So we're going to use the same velocity as the velocity of the inlet, okay? The inlet velocity, that's the flow velocity, 60. So I use 60, 60, right? So that's it for this. Then now I'll apply. After applying, I press close. So this is the various computational boundary conditions we are going to set. Parameters for the boundary conditions we set for the various parts of the computational domain and train body. So for a train body, it's a wall, so we are not going to change any option for the bogie and the train surface, that's the cars. So that's for this. Then the next is to put the reference values. Okay, the reference values. So here we are computing from where? From the inlet to the outlet. Okay, so we click on this place and we choose inlet. Sorry, inlet, not outlet. Inlet. So the area of a high-speed train, normally we assume that is 10 meters per second. Sorry, 10 meters square. Okay, 10 meters square. So, but since our scale is 7, so we must have to divide it by 7 square. So 10 divided by 7 divided by 7 again. So we have 0.20448.